order to do this, we use something called as RNNs. Okay. And there are various versions of RNN that go around in order to overcome the disadvantages, which we'll look in some time. All right. So moving on to the next application, that is GANs. GANs, which stands for Generative Adversarial Network, is an unsupervised part of a deep learning application. Some of the common applications which you can see in recent days is nothing but deep fakes and many more. Finally, coming down to performing classification and regression tasks using multi-layer perceptron. If you remember, or if you're well versed with machine learning, in order to perform classification in machine learning, we had algorithms like decision tree, random forest, or something very simple as linear regression or logistic regression. But let me tell you what, when we try to perform classification using MLP or multi-layer perceptron, we get a very high accuracy even compared to SVM and decision trees. Alright, so now that we know what exactly is deep learning and why we use it, let's now stream down to understand how can we process natural language data using RNNs. So what are RNNs, right? Well, RNN basically stands for recurrent neural network. And we usually use this in order to deal with a sequential data. Sequential data can be something like a time series data or a textual data of any format. So why should one use RNN, right? Well, this is because there's a concept of internal memory here. RNN can remember important things about the input it has received, which allows them to be very precise in predicting what can be the next outcome. So this is the reason why they are performed or preferred on a sequential data algorithm. Okay. And some of the examples of sequential data can be something like time series, speech, text, financial data, audio, video, weather, and many more. Although RNN were the state-of-the-art algorithm for dealing with sequential data, they come up with their own drawbacks. And some of the popular drawbacks over here can be like, due to the complication or the complexity of the algorithm, the neural network is pretty slow to train. And as there are a huge amount of dimensions here, the training is very long and difficult to do. Okay. Apart from that, the most decisive feature for RNN or for the improvement in RNN is that of a vanishing gradient. What this vanishing gradient is that, when we go deeper and deeper into our neural network, the previous data is lost. This is because of a concept called as vanishing gradient. And due to this, we cannot work on a large or a longer sequence of data. Okay. To overcome this, we came up with some new or upgrades to the current recurrent neural networks or RNNs. Starting off with bidirectional recurrent neural network. You see, bidirectional recurrent neural network connect two hidden layers of opposite direction into the same output. With this form of generative deep learning, the output layer can get information from past, future states simultaneously. So as you can see here, we have two layers over here. And as they are bidirectional, what happens is when the algorithm feels that it is kind of losing its gradients or the previous data, it can go back and get the data from the past. So why do we need bidirectional recurrent neural network? Well, bidirectional recurrent neural network duplicates RNN processing chain so that the input process both forward and reverse time order, thus allowing bidirectional recurrent neural network to look into future context as well. The next one is long short-term memory. Long short-term memory, or also sometimes referred to as LSTM, is an artificial recurrent neural network architecture used in the field of deep learning. Unlike standard feed-forward neural network, LSTM has a feedback connections. It can not only process single data point, but also the entire sequence of data. So as you can see here, from what I'm trying to say is, with LSTM or long short-term memory, it has something like, we can feed a longer sequence compared to what it was with bidirectional RNN or RNNs. So why is LSTM better than RNN? We can say that when we move from RNN to LSTM, we are introducing more and more control over the sequence of the data that we can provide. Thus, LSTM gives us more control ability and thus better results. Alright, so the next type of recurrent neural network is the gated recurrent neural network, or also referred to as GRUs. You see, GRU is a type of recurrent neural network that is, in certain cases, is advantageous over long short-term memory. GRU makes use of less memory and also is faster than LSTM. But thing is, LSTMs are more accurate while using longer data sets. I'm sure by now you might have got a hint about the trend that has led to the improvement, right? So the trend over here is, the model should be capable of remembering and taking in on a longer input sequence. The game changer part for the sequential data was developed when we came up with something called as transformers. And this paper was something which is based on a concept called as attention is everything. Alright, so let's take a look at this. The paper, Attention is All You Need, introduces a novel architecture called as transformers. Like LSTM, transformers is an architecture for transforming one sequence into another while helping other two parts, that is encoders and decoders. But it differs from previously described sequence to sequence model because it does not work like GRUs. Okay, so it does not implement recurrent neural networks. Recurrent neural network until now were one of the best ways to capture the timely dependence on a sequence. However, the team presenting this paper, that is attention is all you need, proved that an architecture with only attention mechanism does not use RNN can improve its result in translation task and other NLP tasks. One of the best examples for transformers is Google's BERT. So what exactly is this transformer, right? You see here we have encoder on the top and decoder on the bottom. Both encoder and decoder are comprised of modules that can stick onto the top of each other multiple times. So what happens here is the inputs and outputs are first embedded into n-dimension space since we cannot use this directly. So we obviously have to encode our inputs whatever we are providing here. One slight but important part of this model is the positional encoding of different words. Since we have no recurrent neural network that can remember how sequences are fed into the model, we need to somehow give every word or part of our sequence a relative position since the sequence depends on the order of the elements. Okay, these positions are added to the embedded representation of each words. Alright, so this was the brief about transformers. So let us now move ahead and see some of the popular language models that are available in the market. Alright, so let us now start off by understanding OpenAI's GPT-3. The successor to GPT and GPT-2 is the GPT-3 and is one of the most controversial pre-trained models by OpenAI. The large-scale transformer-based language model has been trained on 175 billion parameters, which is 10 times more than any previous non-sparse language model. The model has been trained to achieve strong performance on many NLP datasets, including tasks like translation, answering questions, as well as several other tasks. Then we have Google's BERT. BERT stands for Bidirectional Encoder Representations from Transformers. It is a pre-trained NLP model which is developed by Google in 2018. With this, anyone in the world can train either their own question answering module with up to 30 minutes on a single cloud TPU or few hours using single GPU. The company then released this showcasing the performance of 11 NLP tasks, including very competitive Stanford dataset questions. Unlike other language models, BERT has only been pre-trained on 250 million words of Wikipedia and 800 million words of book corpus, and has been successfully used as a pre-trained model in deep neural network. According to researchers, BERT has achieved 93% accuracy, which has surpassed any previous language models. Next, we have ELMO. ELMO, also known as Embedding for Language Model, is a deep contextualized word representation that models syntax and semantic words as well as their logistic context. The model developed by Allen NLP has been pre-trained on a huge text corpus and learned functions from bidirectional models, that is BiLM. ELMO can easily be added to their existing models, which drastically improves the features of functions across vast NLP problems, including answering questions, textual intent, and sentiment analysis.
What are GANs? So we are going to start with generative models. So generative models are nothing but those models that use an unsupervised learning approach. In a generative model, there are samples in the data, that is input variables x, but it lacks the output variable y. And we use the only input variables to train the generative model, and it recognizes patterns from the input variables to generate an output that is unknown and based on the training data only. In supervised learning, we are more aligned towards creating predictive models from the input variables. And this type of modeling is also known as discriminative modeling. And in a classification problem, the model has to discriminate as to which class the example belongs to. And on the other hand, unsupervised models are used to create or generate new examples in the input distribution. To define a generative model in layman terms, we can say generative models are able to generate new examples from the sample that are not only similar to the examples but are indistinguishable as well. And the most common example of a generative model is a naive Bayes classifier, which is more often used as a discriminative model. Other examples of generative models include Gaussian mixture model and a rather modern example, that is generative adversarial networks. So let us try to understand what exactly are GANs. or generative adversarial networks. Generative adversarial networks, or GANs, are a deep learning based generative model that is used for unsupervised learning. It is basically a system where two competing neural networks compete with each other to create or generate variations in the data. It was first described in a paper in 2014 by Ian Goodfellow, and a standardized and much stable model theory was proposed by Alec Radford in 2016, which is also known as DGCAN, also known as DCGAN, or we can call it as Deep Convolutional General Adversarial Networks. And most of the GANs today use deep convolutional general adversarial networks. The GAN's architecture consists of two submodels known as the generator model and the discriminator model. So a generator network takes a sample and generates a sample of data. A discriminator network decides whether the data is generated or taken from the real sample using a binary classification problem with the help of a sigmoid function that gives the output in the form or the range 0 and 1. So let us go ahead and take a look at how GANs actually work. To understand how GANs work, let's break it down. So generative means that the model follows the unsupervised learning approach and is a generative model. When we talk about adversarial, the model is trained in an adversarial setting. And network simply means for the training of the model, we use the neural networks as artificial intelligence algorithms. In GANs, there is a generator network that takes a sample and generates a sample of data. And after this, the discriminator network decides whether the data is generated or taken from the real sample using a binary classification problem with the help of a sigmoid function that gives the output in the range 0 to 1. The generative model analyzes the distribution of the data in such a way that after the training phase, the probability of the discriminator making a mistake maximizes. And the discriminator, on the other hand, is based on a model that will estimate the probability that the sample is coming from the real data or not the generator. The whole process can be formalized in a mathematical formula. So G over here is generator, D is equal to discriminator, P data X is the distribution of real data, P data Z is the distributor of generator, X is the sample from the real data, and Z is the sample from generator, where dx is the discriminator network and gz is a generator network. So let's take a look at the flowchart once again, guys. So we have the training data, which is going to give the real sample, and the generator network is going to generate the sample from the random noise or the examples. And then it will go to the discriminator network, where it's going to check if the sample that is coming is real or fake. So that is how a GAN actually works. Now let's take a look at the training phase, like how a generative adversarial network is actually trained. So it happens in two phases, guys. So the first phase is where we train the discriminator and we actually freeze the generator, which means that the training set for the generator is turned false and the network will only do the forward pass and there will not be any back propagation. Basically, the discriminator is trained with real data and checks if it can predict them correctly. And the same with the fake data to identify them as fake. After this, there's the second part where we train the generator and freeze the discriminator. So we get the result from the first phase and we use them to make better from the previous.
Hey, you guessed right. I'm Robin. And listen up. You've got only 6 months. Yep, you heard me right, 6 months to upskill, or you'll be left in the dust. AI is taking over jobs, and it's coming at you faster than you can imagine. You've got two options. You can upskill with Outskill's generative AI program, or you can get extinct. AI could make your job a thing of the past. Look at the number of topics in this program. Build AI assistants and GPTs, no-code AI automation, how to make money with AI, real-world AI applications, unbelievable. So do you want to upskill and be relevant or left behind?
"50% of data scientists and machine learning engineers highlights the importance of applying research in data science. Adding research capabilities to your skill set can make all the difference in your data science and machine learning career. At Scalar, you learn how to read a research paper as part of an industry-ready curriculum. Work on projects built in partnership with top companies. Find out what it takes to publish your own research papers with the help of expert mentors. Get professional advice for scaling your career in artificial intelligence, machine learning, data science, or research science. Take the research game to a whole new level with Scalar's Data Science program.
Anything, but there are a lot of setbacks that can cause a lot of hindrance in its path. Some of the major challenges faced by GANs are, the first one is the stability. So there has to be a stability that is required between discriminator and the generator network. Otherwise, the whole network would just fall. For example, in case, let's say, if the discriminator is too powerful, the generator will fail to train altogether. Won't be able to push fake samples to the discriminator, and it will always identify them as fake. And let's say if the network is too lenient, the discriminator network is too lenient, so any image that would be generated by the generator network would make the network useless. The next challenge that is faced by GANs is GANs fail miserably in determining the positioning of the objects in terms of how many times the object should occur at that location. Suppose we have an image in which we have, let's say, 3 dogs with 2 eyes, and sometimes a GAN will fail to determine the positioning of the objects in terms of it will generate an image with like 1 dog and 6 eyes. So that's kind of a problem that we face while working on GANs. And the next challenge is 3D perspective troubles GANs, as it is not able to understand the perspective also. So it will often give a flat image for a 3D object. So that's one challenge that we face with GANs as well. And GANs have a problem of understanding the global objects, and it cannot differentiate or understand a holistic structure. Like if you're talking about trees or if you're talking about flowers, that's a problem that GANs will follow. And last but not least, newer types of GANs are more advanced that I've talked about, that is deep convolutional generative adversarial networks, and are expected to overcome these shortcomings altogether. So we don't have to worry about these. These are the shortcomings that we face with normal GANs, the initial generative adversarial networks. Now that they have become more advanced, they actually overcome these shortcomings, so you don't have to worry, guys. So last but not the least, I want to talk about a few applications of generative adversarial networks. So the first one is prediction of next frame in a video. So let's say the prediction of future events in a video frame is made possible with the help of GANs, and DVD GAN, or we can call it as dual video discriminator GAN, can generate a 256 by 256 videos of notable fidelity up to 48 frames in length. And this can be used for various purposes, including surveillance, in which we can determine the activities in a frame that gets distorted due to other factors like rain, dust, smoke, etc. So the possibilities are immense with this. If you are able to predict the next frame in a video, that actually helps in a lot of things like surveillance, security, and we can predict outcomes based on these frames that we generate from a video. After this comes the text to image generation. So basically, object-driven attentive GAN, which is also known as object GAN, performs the text to image synthesis in 2 steps. So the first step is generating the semantic layout, and then generating the image by synthesizing the image by using a deconvolutional image generator is the final step. So this could be used intensively to generate images by understanding the captions, the layouts, and refine details by synthesizing the words. And there is another study about the story GANs that can synthesize the whole storyboards from mere paragraphs. So that's actually a very good idea if you're talking about GANs. So you can just give a few layouts and captions. Based on that, it will generate an image for us. Talking about the next application, we have image to image translation. So Pix2Pix is a model which is designed for general purpose image to image translation. So let's say we have 3 images. We have a real image, then we'll be having a generated image, which is basically a fake, and then it will be reconstructed to the previous image, which was real. So this is how image to image translation works, guys. And after this, we have enhancing the resolution of an image. So super resolution generative adversarial network, or also known as SR-GAN, is a GAN which can generate the super resolution images from low resolution images with finer details and better quality. So this is actually a very good application of GANs, guys. The applications can be immense. So you imagine a higher quality image with finer details generated from a low resolution image. The amount of help it would produce to identify details in low resolution images can be used for wider purposes, including surveillance. We can use it for documentation, security. We can use it for detecting patterns, etc. And last but not least, we have interactive image generation. So GANs can be used to generate interactive images as well. And computer science and artificial intelligence library, also known as CSAIL, has developed a GAN that can generate 3D models with realistic lighting and reflections enabled by the shape and texture editing. And more recently, researchers have come up with a model that can synthesize a reenacted face animated by a person's movement while preserving the appearance of the face at the same time. There are a lot more applications we can work on.